In this video, we discuss homogeneous polar differential equations. We'll talk about how to recognize them, then how to solve them, and then we'll do some examples. So there are two ways to recognize a homogeneous polar differential equation. If the differential equation can be written in this form. So if dy dx is equal to a function of y divided by x. So you can get that first derivative by itself, and you can write the rest of the differential equation. You can write this right-hand side as a function of y over x. So it might have a y over x squared in it. It might have a sine or cosine of y over x. It might have a y over x cubed. If you can write the differential equation in this form, it's homogeneous polar. Now, another way that you might recognize it is if you can write the differential equation in this form. Now, if the first derivative of y with respect to x can be written this way, if that's true, and g and h are what are called homogeneous functions of the same degree, and I'll tell you what that is in a minute, then the differential equation is a homogeneous polar differential equation. Now, equivalent to this last one is this. If I multiply both sides by h of xy, and I multiply both sides by dx, and then I rearrange these just a little bit, sometimes you'll see a homogeneous polar differential equation written in this form. So you've got some function of x and y times dx plus a function of x and y times dy equals 0. And don't worry too much about that sign. I could have a plus there because that negative could be distributed in here. But the idea is if the first derivative can be written as this quotient where g is a homogeneous function of 1 degree and h is a homogeneous function of the same degree, then the differential equation is a homogeneous polar differential equation. Or you could take that and rearrange it. If this function is a homogeneous function of a certain degree, and this function is a homogeneous function of the same degree, then this is a homogeneous differential equation. And it turns out that if these are both homogeneous functions of the same degree, this right-hand side can be rewritten this way. It can be written as a function of y over x, and we're going to show that. So let's talk about what a homogeneous function is. We'll say that f of xy is a homogeneous function of degree n if the following is true. If f of xy is t to the n, or excuse me, f of tx and ty is t to the n times f of xy. Now this notation looks a little odd, but all it is us substituting tx for x and ty for y. If you make that substitution and you can factor out a power of t from that function, then that function f is a homogeneous function of degree n. So here's an example. Let's say you have f of xy equals xy plus y squared. If I want to determine whether or not that's a homogeneous function of degree n, or a homogeneous function in general, I just replace all of the x's with tx's, and I replace all of the y's with ty's, and then I simplify. You've got t times t is t squared, and you've got an xy here. And if you've got a product inside, you're squaring the t and you're squaring the y. Then I look at both of these terms and I factor out the highest power of t I can. They have a t squared in common, so we'll factor that out. And I'm left with an xy plus y squared, and that was my original function. So since this function, or since f of tx and ty can be written as t squared times the original function itself, that implies that f, or that's equivalent to really, that means that f is a homogeneous function of degree 2. And the degree is that power of t right there. Now here's another one. Say we've got g of xy equals negative x squared plus 5y cubed. The question is that a homogeneous function? Well, one way I can figure that out is I can just replace x with tx, and I can replace y with ty. Do a little bit of algebra, and then we'll see, can we factor out a power of t? Well, we've got -1 times this. If you're squaring a product, you square each factor separately. If you're cubing a product, you cube each factor separately. And then you look at both of these guys and you say, well, what's the highest power of t I can factor out? I can factor out a t squared. So I've got t squared times -x squared plus 5, and that was a t cubed. So I'm still left with an extra t, 5t times y cubed. So that's t squared, but this function over here is not the original function because it has that extra t. And there's nothing I can do about that extra t. If I factored out t cubed from everything, I'd end up with an extra t in the denominator over here. So this is it. It doesn't go any further. I cannot write this as t to some power times the original function. So that would imply that g is not a homogeneous function. Now let's think about these two functions and think about why it was possible for us to factor out that t squared. And this is pretty easy to figure out when you're dealing with polynomial functions. That is an x to the first times y to the first. So if I'm trying to find the degree of this, I just add the exponents. That's a degree 2 term. And y squared is a degree 2 term for a polynomial. So both of these have degree 2. So when I replace the x with tx and the y with ty, because this had degree 2 and this had degree 2, I'll end up with 2 t's from that and 2 t's from that, and I'm able to factor out the t squared. So since this was a polynomial of degree 2, where every single term was degree 2, this turned out to be a homogeneous function of degree 2. Now, when I look at this, I think it's not a homogeneous function. And the way that I know is that this is a degree 2 term, so it's going to have a t squared in it after I substitute tx for x. And that's a degree 3 term. It's going to have a t cubed in it. So if that's degree 3 and that's degree 2, the whole thing, well, the whole thing is not a homogeneous function of a single degree. It's not a function of degree 2, because this one has degree 2 and that one has degree 3. So g is not a homogeneous function at all. Let's look at one more. You might ask yourself, what about this function? Is this function a homogeneous function? Well, the question is, can you replace x with tx and y with ty and factor out a power of t from everything? Well, just to figure that out, let's try it. Let's replace x with tx and y with ty. The t's reduce. And now I've got a tx plus ty times natural log of y over x, and I can factor out the t from both of those. So I have t times the quantity x plus y natural log of y over x. T times x gives me the first term. T times this quantity gives me this quantity. And that's t times the original function. Look, that the function right there is the original function h. And of course, that is an implied 1. So this is a homogeneous function of degree 1. Remember, the degree is that power of t. Okay, so now let's go back to homogeneous differential equations and think about how this is related. So we said here, if dy dx can be written this way, where g is a homogeneous function of a certain degree, and h is also a homogeneous function of the same degree, then dy dx equals this is a homogeneous polar differential equation. Now, sometimes it's not written this way, it's written this way instead. But in the same way, I'm looking at this function and I'm looking at this function and I'm asking myself, are they homogeneous functions of the same degree? If they are, then the differential equation is homogeneous polar. Now, I claimed that if the differential equation can be written this way, it can also be written this way. So if these are homogeneous functions of the same degree, according to this, that means I can rewrite this right-hand side as a function of y divided by x. So let's look at a differential equation and see if we can recognize whether or not it's homogeneous polar. And then if it is, let's write it as a function of y over x. So let's say we have this differential equation. X plus e to the y over x times dx minus x times e to the y over x dy is equal to 0. So the differential equation is written in a slightly different form this time. But we can divide everything by dx, divide every term by dx, and of course 0 divided by dx is just 0. And then we can solve for dy dx. So I'll subtract this guy from both sides. And I'll divide both sides by that guy. And of course, the negative over the negative is a positive. And the question becomes, is this a homogeneous function? Well, I could focus on this, think of this as a homogeneous function or as a possible homogeneous function, and this one as a homogeneous function. If these are homogeneous functions of the same degree, the differential equation is a homogeneous polar differential equation. Or when I was given this one, I could just focus on this function and ask myself, is this a homogeneous function? I'm gonna need a label. I'm just gonna use m and n here. So I'll call that m of xy and this n of xy. So m of xy is x plus e to the y over x. The question is that a homogeneous function? Well, let's replace x with tx and y with ty. Well, ty over tx is just y over x. And we end up with tx plus e to the y over x. Now, there is not a common factor of t in this term and this term. So I can't factor out a t to the first and say that this is t times this. This one's actually really misleading. If you're not very careful with your algebra, you might think that this is t times m of xy, but it's not. That t is only applied to the x. It's not applied to this whole thing. We need that t to be here, and then all of this to be in parentheses in order for that to be t times m. But it's not. That t is just applied to the x. Since that is not t times that function, it is not the same as t times this, which is t times m. Since those are not the same, m is not a homogeneous function. And since m is not a homogeneous function, that means the differential equation is not homogeneous polar. So the method that we're going to learn in this section won't work for this differential equation. Now, obviously, this is a nonlinear differential equation. You've got a function of y multiplying that dy dx. Look at, if I get that dy dx by itself, and I have this function on the right-hand side, it's not separable. I'm not able to write this as a function of x times a function of y. Actually, let me think about that. No, actually, I can't. I can't do that. So it's not separable. It doesn't look like it's linear. It's not linear in y anyway. And if I were using x as a function of y, it's not linear in x either. So far, none of the methods that we've talked about in our course would allow us to solve this differential equation. There might be another method later, but for right now, we can't solve this one. So the differential equation there is not homogeneous polar. What about this one? All right. Now, this is already written as a function of x and y over a function of x and y. The question is this a homogeneous function? And then if so, what's the degree? And is this a homogeneous function? And if so, what is the degree? Well, since these are polynomials, it's actually pretty easy to check. This is a homogeneous function of degree 3, because if I replace the x with tx and I replace the y with ty, I'm going to end up with a t cubed term here and a t cubed term here that I'll be able to factor out from the whole thing. So this function can be rewritten, or this function evaluated at tx and ty can be rewritten as t cubed times the original. Now let's look at this guy down here. I've got an x squared times a y to the first. Well, that's a degree 3 term because we add the exponents, the 2 and the 1 gives us a 3. And this is also a degree 3 term. It's at x to the first times y squared. So we have the 1 and the 2 and we get the 3. So if I replace the x with tx and the y with ty here, I'm going to have a t cubed that comes out of that product. And I'll have a t cubed that comes out of this product as well. So this is a homogeneous function of degree 3. And this is a homogeneous function of degree 3. And that means this differential equation is a homogeneous polar differential equation. Now, I didn't write it down. I didn't confirm it algebraically, but you should check for yourself if you're not sure. These are homogeneous functions of the same degree, so the differential equation is homogeneous polar. Now, just to clarify, this is only a homogeneous polar differential equation if the degree of this function, the degree of this homogeneous function, and the degree of this homogeneous function are the same. So if this one happened to be homogeneous in degree 3 and that one happened to be homogeneous in degree 2, it would not lead to a homogeneous differential equation. So you want to be careful about that. They have to have the same degree. Now, the claim is that if these two guys are homogeneous functions of the same degree, then this function on the right-hand side can be rewritten as a function of y over x, or x over y. Either one would be fine. So now I've got to do a little bit of algebra. I'd really like this, instead of being a y cubed, I'd like it to be a y cubed over x cubed, or a y over x cubed, so that it matches that form. In order to make that happen, I just have to divide. I'll divide the entire numerator by x cubed. That'll give me the y cubed over x cubed that I want to give me a y over x quantity cubed. And that's legal as long as I also do the same thing in the denominator. We're dividing by x cubed there as well. X cubed over x cubed is 1. Then we've got y cubed over x cubed. And here's the rule from algebra that you might need. Actually, let's use a. We've got a to the n over b to the n is the same as a over b to the n. So y cubed over x cubed is y over x quantity cubed. And then down here you've got 9 times x squared y plus 2 times xy squared. And we're dividing everything by x cubed. I'm dividing by x cubed here and x cubed here. And 2 of the x's reduce there. 1 of the x's will reduce there. And so we end up with 1 minus 5 times y over x quantity cubed, all divided by 9 times the quantity y over x, plus 2 times y squared over x squared, which is the same as y over x squared. Oops. So now this right-hand side is written as a function of y over x. So I've got y over x cubed, y over x to the first, y over x squared. And there are no extra y's or x's around here. There are no extra y or x terms that aren't in a y over x. This is a function of y over x now. Now, I haven't proven it, but I claim that if this is a homogeneous function of a certain degree and this is a homogeneous function of the same degree, you can always write this right-hand side as a function of y over x. And in practice, what you're going to do algebraically is you're looking for whatever power y is raised to in the numerator, and you're trying to make that look like a y over x raised to that power. So if this is a y to the 4th, I would divide everything by x to the 4th. If that was a y to the 5th, I would divide everything by x to the 5th. And that would work in getting me a result that looks like this, because in both of those cases, everything would simplify. Now, the degree here, the degree that you're dividing by, we're dividing by x to some power, it turns out to always be the same as the degree of the term or of the homogeneous functions themselves. So this is a degree 3 homogeneous function, and so is this. So it turns out we're going to divide by x to the 3rd. Okay, so now we know how to recognize a homogeneous polar differential equation, so we're good there. And the question is, well, how do you solve them? Well, if you have a homogeneous polar differential equation, it turns out that if you make a substitution, you can write all of this entirely in terms of 2 variables, not y and x, but v and x, where v is y divided by x. So you're going to write this in terms of v and x. It's going to be separable. You're going to separate the variables, and then you're going to back substitute. So it's actually a pretty simple process. But let's write it down step by step. So the first thing you always want to do is verify that the differential equation is homogeneous polar. If it's not homogeneous polar, no amount of substitution is going to work. This method will fail if the differential equation is not homogeneous polar. So first we verify that it's homogeneous polar. And then if it is, then you want to write the differential equation in this form. So you're going to have the derivative on one side, and you want to write that as a function of y over x. So we're going to do some algebra. We're going to get to this point. Then the claim is that this function, or that this differential equation, is separable in terms of x and v, where v is y over x. So we're going to let v equal y divided by x, then solve that for y. So y is v times x, or x times v. And you want to think of v as a function of x. So that's not v times x, but that's v as a function of x. Well, if y is equal to x times v and v is a function of x, then you want to compute dy dx, because we've got that in our differential equation. And when I compute dy dx, I have to use the product rule. That's my first function, and that's my second function. So we're going to have, according to the product rule, derivative of the first with respect to x, which is 1, times the second, plus the derivative of the second with respect to x, which is dv dx, times the first, which is x. So you know what dy dx is in terms of v and x, it's that right here. And you know what the right-hand side is in terms of v. You're going to replace every y over x with v. And so then you're going to have a differential equation that is separable in terms of v and x. So you want to substitute all of these pieces up here. So dy dx is going to be replaced, and every y over x is going to be replaced by a v. So dy dx is replaced by v plus dv dx times x. And then this side over here, well, that's just going to become f of v. And the claim is that this is always separable. So you want to separate the variables. So what we need to do to separate the variables for this guy in general is first subtract the v from both sides. I think I want to take reciprocals as well. So I'm going to write that as x over 1. I'm going to write this side as f of v minus v over 1. And remember, that's not f times v. That is f as a function of v. We're going to flip it. So we'll have 1 over x times dx dv equals 1 over f of v minus v. And then we want to multiply both sides by dx, or excuse me, dv. Because I want all of my v's on one side and all of my x's on the other. Now again, I'm kind of treating that like a fraction. It's not a fraction, but dx dv times dv by definition is the differential of x. So we can do that, even though technically this cancellation is, I'm doing a little bit of hand waving there. Okay. So I've got all my x's on one side and my functions of v on the other, and then we'll anti-differentiate both sides, and then we're going to get a function of x equals some function of v. So we'll solve this separable equation by doing just this. And then after you do that, back substitute. So you're going to replace v with y over x, because that's what v was. V was just something we made up so we could make the differential equation separable. And then after you replace v with y over x, you have an implicit solution. Of course, you're going to simplify. And then if you can, you want to solve for y to get an explicit solution. Now these are generally nonlinear differential equations. So what we're getting is a family of solutions. It is not necessarily the general solution. Nonlinear differential equations don't have the nice, beautiful theory that linear differential equations have. With linear equations, it's often, we're often sure that we have a general solution. With nonlinear equations, we might miss a solution. It might not be a member of the family. Okay, now I know this seems like a lot, but the idea is this. If the differential equation is homogeneous polar, then every single time your goal is to write it as a separable differential equation in v and x. So we verify that the differential equation is homogeneous polar, and then we're going to make a substitution. And that's all of this, these 4 steps. We can just say we are letting v equal y over x, which means that y is equal to x times v, which means that dy dx is derivative of the first times the second plus derivative of the second times the first by the product rule. So we verify that the differential equation is homogeneous polar. We make this substitution. So you write the dE in terms of v and x, and then it's separable. And you solve the separable equation. So the whole point of the method is to take your homogeneous polar equation, make a substitution so that it's separable. And once you make the substitution and you separate the variables and solve it, all you have to do is do this last step, which is back substitute. Because v is equal to y over x by design. And we say, well, why is that design okay? It's because the differential equation is homogeneous polar. If the differential equation is not homogeneous polar, none of this is even possible. Okay, so that is the summary of the method, the big picture. You recognize it is homogeneous polar. You let v equal y over x. Then the differential equation will be separable in v and x. Solve that differential equation for a function of x set equal to a function of v plus c. And then you've got an implicit solution. So you back substitute and you're done. Let's actually apply this now. There we go. So I have xy plus y squared dx. Oops, I want to do minus y, or minus x squared times dy is equal to 0. Now looking at this, I can already see that it's homogeneous polar because this is a homogeneous function of degree 2. So I've got that x to the first times that y to the first and a y squared. So that's degree 2 and that's degree 2. So this is degree 2. And then this guy is also degree 2. So just to verify, I'm going to let m equal this function and let n equal this function. And the first thing I do is verify that m and n are homogeneous functions of the same degree. And because they're polynomials, I kind of already know the answer. But we should verify it on paper, just so that if a reader is looking at our work, they can follow along. It's not enough just to know how to do it yourself. we have to know how to communicate it with other people. So we're going to replace x with tx and y with ty, and then simplify. We got a t times t there, that's t squared times xy. And when you're squaring a product, you square each factor separately. Factor out the t squared, and you've got t squared times xy for the first term, and then t squared times a y squared for the second term. Well, that's t squared times the original function m. So m is a homogeneous function of degree 2. The question is this also a homogeneous function of degree 2? I think you can see it. I hope you can see it. You replace x with tx, you replace y with ty. Square the t, square the x, factor out the t squared, and then you see you've got t squared times negative x squared, and negative x squared was n by definition. So we have n, and it is a homogeneous function of degree 2. Since that's true, the differential equation is a homogeneous polar differential equation. So we'll say since m and n are both homogeneous functions, and I'm just using FNS for functions, it's an abbreviation, of degree 2, or you could just say of the same degree, that's the important part. The DE is homogeneous polar. Okay, now that we know it's homogeneous polar, we can solve it using the substitution. So we can let V equal y over x. Oh, actually, before I do that, we need to start here. Let's write the differential equation in the following form. dy dx equals f of y over x. So if you wanted to, rather than doing this, you could solve for dy dx and do this step first. That would also confirm it. And that'd be good because it's the first step in the method anyway. Got xy plus y squared times dx minus x squared times dy equals 0. Let's divide everything by dx. Of course, 0 divided by dx is just 0. So we end up with xy plus y squared minus x squared dy dx equals 0. Trying to isolate this guy, so we're going to subtract this guy from both sides and divide by x squared. Or divide by negative x squared. Negative divided by a negative is, of course, positive. And we see a homogeneous function of degree 2 divided by a homogeneous function of degree 2. So we know this is a homogeneous function. Now we'd like this to be written as a function of y divided by x. Since these are degree 2 polynomials, and I'm really focusing on this y squared term, I really like that to be y over x quantity squared. So that's a function of y over x. I'll divide the numerator and denominator by x to the second power. In general, to do this, once you get that function of x and y on the right-hand side and that dy dx on that left-hand side, once you're here, so after you've isolated dy dx, you want to divide the numerator and denominator by x to the n, where n is the degree of those homogeneous functions. That's degree 2, that's degree 2. So divide everything by x to the second power. Degree 2, something else that's degree 2. When you do that, it's going to simplify that right-hand side to be a function of y over x. So we have xy divided by x squared plus y squared divided by x squared. And then, of course, x squared divided by x squared. Actually, we had a monomial in the denominator. We could have just divided each of these guys by the monomial. It's the same thing. Okay. X squared divided by x squared is just 1. And one of those x's will reduce with that x there. So we'll have a y over x here. And then y squared over x squared. Remember this rule? Well, that's the same as a over b raised to the n. So y squared over x squared is actually y over x squared. Okay, so that's our first step. We write dy dx as a function of y over x, and then we're going to let v equal y over x. And then we want to write everything up here in terms of x and v. We don't want any y's anymore. We just want x's and v's. Check out what happens. Oops. So we're letting v equal y over x, which means that y is x times v. If we multiply both sides by x, we get y equals x times v. And if v is a function of x, then if I use the product rule to take the derivative of y with respect to x, I get the derivative of the first, which is just 1. Derivative of x with respect to x is 1, times the second, plus the derivative of the second, times the first. So you know if v is this, then y is this, and that's your derivative. And then you're going to take all of these pieces and you're going to substitute in up here. Okay. And we keep going. So the left-hand side of our differential equation was dy dx. In terms of v and x, dy dx is v plus dv dx times x. This is the same as this because of this, because we're applying the product rule to that product over here. And v is y over x, so that's v, and that's a v squared. So we've got that equals v plus v squared. And we want to solve the separable equation now. This will always be separable in terms of v and x. So we're going to subtract v from both sides, so those guys are gone. I need that dx to be multiplying a function of x, and I need the dv to stay in the numerator. So like I don't want to divide both sides by dv to get the v's over here, because I can't have a v squared times 1 over dv and integrate it. I need the dv to be in the numerator and the dx to be in the numerator. Since I need this in the numerator and this in the numerator, I'm going to write this as a fraction and this as a fraction, and I'll flip them. And that's perfectly legal because the derivative of v with respect to x turns out to be or 1 over the derivative of v with respect to x is the same as the derivative of x with respect to v. So it acts exactly like a fraction even though it isn't a fraction. And we've got that right there. Well, it's a fraction involving a limit, but anyway. So we're here. We flip the numerator and denominator. And now I've got a 1 over x times dx on this side, and I need that dv on this side. So I'll multiply both sides by dv. And then it's like these guys cancel out. And we get 1 over x dx over here equals 1 over v squared times dv. Now don't tell me that the antiderivative of 1 over v squared is the natural log of v squared. A lot of students do. If that power is anything other than a 1, and it is, it's a 2, we need to bring that up to the numerator. Remember how that works. If you've got x to some negative power, it's 1 over x to the same power but positive. So I'm using it in this direction. 1 over v squared is the same as v to the negative 2. That I can use the power rule on. That's what you will always do if that power is anything other than a 1. Okay, so now I've got this side is entirely involving x, and this side is entirely involving v, and the dx is in the numerator and the dv is in the numerator, which is very important. Then you anti-differentiate both sides with respect to the appropriate variable. We're just solving the separable equation. The antiderivative of 1 over x is natural log of the absolute value of x. Over here, we're going to add 1 to the exponent and divide by the new exponent. Dividing by -1 is the same as multiplying by -1. Don't forget to add c. So we just solved the separable differential equation. And the last step is to back substitute. Don't forget, v is something that we made up so that we could solve this differential equation. So you're just going to replace v with whatever it was in terms of y and x. And by design, we chose for v to be equal to y over x. So we've got natural log of the absolute value of x here minus 1 over v plus c. And if v is y over x, that means 1 over v. It's going to take that fraction and flip it. That's going to be negative x over y. And if I want to get y by itself, I think I'll just subtract this constant from both sides. And let's take reciprocals again because I want that y to be in the numerator. So I'll end up with y divided by negative x equals 1 over natural log of the absolute value of x minus c. And then to get y by itself, I'll multiply both sides by negative x, which is of course the same as negative x over 1. So end up with negative x over natural log of the absolute value of x minus c, or if you prefer, and some people prefer, multiply the numerator and denominator by -1. You end up with c minus natural log of the absolute value of x in the denominator. So this is a solution. A couple of things. We probably want an interval of existence. And let's look at our method. We started here, and we never want to divide by 0, right? And I know we're kind of cheating there with that dx, like infinitely small. It's not 0 though. So x can't be 0. V can't be 0, and v is y over x. If v can't be 0, that means y can't be 0. Well, this was never going to be 0 anyway, and x can't be 0 because of this log. So it looks like this is going to be well defined on a 0 to infinity. X equals 0 is a problem. Well, actually, no. Let me check just one more thing. This would be 0 to infinity if that was just a log in the denominator. But actually, the whole denominator cannot be equal to 0. So c minus natural log of x is not allowed to be 0. So natural log of x is not allowed to equal c. So the absolute value of x is not allowed to equal e to the c. So I guess we're going to have a problem whenever the absolute value of x is equal to e to the c, or whenever x equals plus or minus this e to the c, where c is that denominator. So it really depends on where that is relative to x equals 0. This function is well defined on 0 to infinity. Well, we know that e to the c is positive. So if x is equal to e to the c, we're going to have a problem. So our solution will be well defined on the interval from e to the c to infinity, not including that e to the c. We'll also have a problem when x is equal to negative e to the c, just some positive value over, or some positive value times -1, so that would make that a negative number. It's over there. But if I'm treating x to be greater than or equal to 0, this domain would have to be e to the c to infinity. So that's one possibility. The other possibility is that, well, we can take the log of a positive number, and this is always going to be positive except when it's 0. So we're still going to have a problem with x equals 0 here. But maybe the y values are negative, or maybe the, I guess maybe the input values, the x values here are negative. So I guess we would be fine also on this interval from -infinity to negative e to the z. I said e to the c is what I meant, not e to the z. So one of those is the maximal interval of existence. Those details aren't too important, but we always like to know what the domain of our function is, or that maximal interval of existence of our function. Okay, so that was our first example. I think I'll make another video for the second example. So let's just go through the method briefly. First, you look at your differential equation and you recognize whether or not it's homogeneous polar. And we've got that shortcut. If these are polynomials in x and y, you can just determine whether this is a homogeneous function of a certain degree. And if this is a homogeneous function of the same degree, then the differential equation is homogeneous polar. So we confirm that. Then we write our differential equation in this form. We want dy dx to equal a function of y over x. We do a little bit of algebra and we get here. And then we say, okay, I'm going to let v equal y over x. So this is v plus v squared. And then I need to write dy dx entirely in terms of v and x. So since v equals y over x, y is equal to x times v, where v is a function of x. Take the derivative of y with respect to x using the product rule. And then you can replace this guy with this in terms of v and x. So this gets substituted in here, and this gets written in terms of v. So now you've got a differential equation entirely involving x and v, and it will always be separable. So you want to get all the x's on one side, all the v's on the other, anti-differentiate, and that gives you the solution to the separable dE. And then you back substitute. And at this point, if I just asked you for an implicit solution, or y is not by itself, you're done. You can stop here. We've got an implicit family of solutions. Now, if I want to get y by itself, I've got to do a little bit of algebra. We did the algebra to get y by itself. This is an explicit solution. Explicit family of solutions. And we've found the maximal interval of existence in a couple of cases, depending on whether we're interested in negative x values, which would be over here, or positive x values. Now, if you're given an initial condition, if you're given a positive x value, you would use this one. And if you're given a negative x value in your initial condition, you'd probably use that one. In the absence of that information though, either this one or this one would be fine for your interval of existence. So that's the method, guys. We'll do another example in the next video.